Hello everyone, my name is Kamal, and in this video I will discuss one problem which came in CSIR exam, and this is based on Hermitian operator. So let's start. This question came in December 2011, and so the question is like this: identify which of the following operators is not Hermitian. So they have given four options. Okay, so before solving this problem, let me introduce what is an operator. An operator is nothing but a mathematical instruction which we do on functions. So basically in quantum mechanics the functions are nothing but your wave functions, and operators will be mostly involve differentiation and integration. Fine. So there are various operators and we are not interested in all of them except Hermitian operator in quantum mechanics, because Hermitian operators produce real results. So in quantum mechanics we say that the eigenvalues of the Hermitian operators are real. What does it mean is that, so if you want to measure energy, position, velocity, kinetic energy, so these all has to be positive number, a real number. So it cannot be an imaginary number. Okay, so to ensure that we have to use Hermitian operators. Now there is a condition for any operator to be Hermitian operators, and the condition I have given in the orange box. Now if you see the orange box, it is clear that you have to evaluate integrals. You evaluate the integrals on both sides, left hand side and right hand side, and finally see if both of them are equal, then this operator is a Hermitian, otherwise not. Okay, but there is also another way to solve this problem. So the quantum mechanics start with two important operators, and all other operators can be derived with the help of these two operators. So these two operators are position operator and momentum operator. Anything with a cap is known as operator. Okay, so the position operator is nothing but x multiplied by and the momentum operator is slightly involved, so it has a h cross divided by I del by del x. So you're dealing with only one direction, x. Now because these operators, quantum mechanics are based with these two operators, so these two operators has to be Hermitian operators. In other words, these two operators are defined in such a way that they has to be Hermitian operators. So you can evaluate them and you can ensure that these two are Hermitian operators. But you can confidently believe that because the quantum mechanics is based on these two operators, position and momentum, so these two operators has to be Hermitian operator. Now if you see the option A, this is nothing but your momentum operators, so the option A has to be Hermitian operators. Now if you see the option D, which is x square, now if you square the position operator you get a x square. Now if you square the momentum operator you will get a px square, which is equal to minus h cross square del square by del x square. Now if you square any Hermitian operator, the square will also be Hermitian in nature. So the x square you can also derive very easily if you use the condition I have given there in the orange box. If you see at the bottom, it is very easy to do that. So the x square is also Hermitian operator. That means option A and option D are Hermitian operator. Okay, now Since momentum operator is a Hermitian operator, its square is also Hermitian operator. Okay, now if you see the operator very carefully, this is nothing but minus h cross square del square by del x square. Now, so the momentum operator, square of the momentum operator uh, is simply, I mean, some constant, and you have del square by del x square. So you can bring the constant to the left hand side also. If you bring the constant to the left hand side, then you will be ending up with only del square by del x square. Okay, okay, that means there is a theorem in quantum mechanics which says like this: if A is a Hermitian operator, then CA is Hermitian if C is real, and it is not Hermitian if C is imaginary. Now, del square by del x square is nothing but some constant into square of the momentum operator. Now, momentum operator is a Hermitian operator, and the constant is a real number, so minus h square. It's just 1 by minus h square, h cross square. So this is a real number, so that means d square by del x square is also a Hermitian operator. Otherwise, you can think in this way, that px square is nothing is there except some constant and dx square. So if px square is a Hermitian operator, then del square and del x square has to be Hermitian operator. Now, uh, now since d square dx square is a Hermitian, d square by dx square is a Hermitian operator, and if I multiply an imaginary term I, then it's not a Hermitian operator. This is according to the theorem. So this option B is I d square by dx square is not a Hermitian operator. Okay, so this is kind of, you have to believe that this position and momentum operators are Hermitian operators, and their square is also Hermitian operator. So from there you can easily prove for this question. Still, I will encourage you guys to solve this problem using the condition of Hermitian operator, because this will test your knowledge of integration. Solving a problem is not a very great thing, but understanding a problem is more important than solving a problem. Okay, so I'll encourage you guys to solve this problem with the help of integration. It's a simple higher secondary mathematics. So thank you guys. So if you guys have any more problem, I'll be happy to answer that. Bye bye.